Hello everybody, Stoner Dave here, and today's video is going to be kind of a longer one. It's kind of a mismatch of some things that I've done over the weekend. So for those of you that don't know, which if you're watching this, you probably have never heard of the guy before, there's this dude on the internet named John Mandlbaur. Now, Mr. Mandlbaur feels that he has proven oh, excuse me. He feels that he has proven a nearly 400-year-old theorem wrong. This is a theorem so fundamental to physics, it's actually called a law. Now, this law is called the law of conservation of angular momentum. Now, the law says that when in a state of equilibrium, that means there are no external forces, no external torques, an object will maintain a constant state of angular momentum. That means if it's spinning, it's going to keep spinning. If it's spinning like in an orbit, it's going to keep going in that orbit. As long as there's nothing pulling on it or pushing on it or anything like that, right? It'll just keep spinning and going around. This law is actually the basis for Newton's laws of motion. I mean, if you look at the way Newton wrote the famous force equals mass times acceleration equation, he actually wrote it as a change of momentum. And it was based completely and totally on the idea that angular momentum is always conserved. And he reasoned this because at this time we'd already discovered that the Earth is going around the sun. We just didn't know how and why. He determined that unless acted upon by a force, everything will move in just a straight line. So he reasoned that gravity must be the force that pulls everything down. And then he did his force equals mass times acceleration based on, well, if angular momentum is conserved, then the force will be equal to the mass times the change in momentum. Actually, it's mass times acceleration, right? Acceleration is the change in velocity. Momentum is mass times velocity. So if you look at it, it's actually the change in momentum. What is it? Change in momentum times the acceleration. No, it's momentum is mass times velocity. Acceleration is the change in velocity. So that means that altogether force is equal to the change in momentum. That's it. Mass and velocity, change in velocity is acceleration. Bada boom, bada bing. Newton invented calculus, and this is how he solved what the gravitational constant is. And it's very close to what we get when we use Einstein's formulas. But Einstein's formulas are so complex that it takes a lot to get to them. I mean, it's great for things like Mercury, which doesn't seem to follow Newton's predictions as far as its orbit, you know. And that's what Einstein fixes. It fixes those high gravity areas, you know. Now, what John is discussing is a simple ball on a string. Now, in a physics classroom, they may demonstrate this to show you a conservation of angular momentum. But the more common example that is used is the person sitting on a chair with some dumbbells in their hand, you know, like 1, 2, 5-pound dumbbells. They hold them close to their chest, get spun around. And while they're spinning, they put their arms out and they slow way down, right? Like almost stopped, right? And then they pull their arms in, they speed way up. Now, if you were to take this person and you notice that they're carrying equal weights on equal sides, so they could hold it like this too, but what that would do is it would create this unbalancedness, and it would cause the chair to start wobbling because that force is too much on the one side. But only like this with the weights on the outside, you could still use the same moment of inertia to do your equations. And you'll find that if you were to spin somebody around going at a rate of 120 revolutions per minute, that's pretty fast, right? It's pretty fast. So if the person is able to pull their arms in at that speed, you know, that's going to be a question. But if the person were to pull their arms in, they would actually, what would happen is right about halfway into their rotation, that chair is going to be going so fast that it's going to go out of control and it's going to fall over. There's going to be just too much. It would have to be too perfectly balanced for it to be able to handle that. But we are able to calculate, and the chair has grease going around the ball bearings where it's rotating to eliminate friction. Yeah, there's a reason why those ball bearings and everything on the chair to allow it to rotate are there. You know, you got the springs to hold it up when you sit down on it. All these things are to keep the chair in a state of equilibrium while you're sitting on it. Think about that. They don't want you to be moving around unless you kick the chair to the side, you spin the chair around. They want you to be in a state of equilibrium in that chair. That is why the chair is used in physics classrooms and not a ball on a string. Now, here's the fun part. Even though that ball on a string has got a lot of outside influences on it that actually create a lot of stopping of the ball, right? My contention is that the friction force is going to be extreme in the situation because you're dealing with a small mass going around a radius with a string being pulled with tension, and that tension on the string is actually pushing down on the point of rotation, and it's pointing down depending on how much that mass is, how fast it's going, and more importantly, it's got gravity on it as well. So there's really some extra components, and you'll notice that depending on how fast you spin that ball, it's not going across a flat plane. You know, like if you were to use this post here, back here, and imagine that as a straight line going across the screen, and that were to be your x-axis, that ball is actually going to be swinging around somewhere around this kind of a position. You know, if we were to consider this the halfway point, that ball would be swinging down here, not up here, and that's because gravity is pulling it down. The faster you spin it, the less gravity is pulling it down, because the more that tension force is trying to pull it in the x direction. You'll notice that the x component is much larger than the y component. And that being said, the x component is equal to the sine of the theta times the total tension. So in order to be able to get that ball all the way up so that it would be level, you'd have to be exerting enough tension in the x direction that you can counteract the effects of the pull of gravity in such a way that as the cosine of 90 approaches 0, right? Because the gravity component is going to be equal to the total tension times the cosine. So the closer that angle gets to 0, the closer that tension has to get to infinity. That's kind of calculus talk, right? We're talking about a limit, right? So let's consider this is the center of our center of rotation, and this pull, which is 90 degrees off here, right? So that represents the where the ball is supposed to be. But in actuality, and I'm sorry I have to do this, so we can't really travel down this pole right here, and you'll be able to see it. We'll use this right here because this is orthogonal to our y, and it's in the z coordinate. We can rotate that 90 degrees, and we can call that our y direction as well. This would have to be we'll reference this as being towards the ground. I know it's towards the top of the screen, but you know, we can go this way too. Okay, so we'll use this right here as being towards the ground, and you can see we got kind of a representation of the ground, but not really. So this ball, we'll call this point where my finger is, that's 0.000, right? And I know it looks like I'm following this down, but I'm really following this down. This is our y plane, right? So this is our y. This is our x. This post right here would be actually our z, right? But because of how we're sitting, it's going along with our y actually. So that's actually kind of good for our demonstration here. So if the ball is going out, we'll call this first ring right here 1 meter, right? So the ball's going out from here to here. It's rotating, but it's not going to be along this plane. It's actually going to be a slight dip below it, right? Which actually it shortens up the graphically, you know, because the rotation's in the z coordinate. So although it appears to change if we were to go along a radius here, the distance appears to change. It's actually it's still the same distance from the center. So, and that's why it is, because as you can see, if we were like right here flat, there's no fall in the y direction. Now the fall in the y direction, there has to be that force of gravity there. You can't get rid of gravity. That's mass times the rate of gravity, which is we use 9.8 meters per second squared. So that little dip that's there, right? No matter how fast you go, and there's still a little bit. The closer that it gets to zero, the more that tension gets increased up towards infinity. Because you have to think, the cosine of 90, which it's 90 degrees off here, right? We use cosine because if this is 0, right? The sine of 0 is 0. And that would be the only way for it to be down there, is if it was going 0. So we use the sine of theta times that total tension. We know that the cosine of theta times the tension, right, it's going to equal the mass of the ball times gravity. So we're going to write that down, and we're going to look, and we're going to say, okay, so we've got that. We also have an equation to calculate the tension in the x direction, and that comes to us from our kinematic equations, where we study the rotation in the x direction. And what it tells us is that the tension in the x direction is going to be equal to the mass of the ball times that velocity that it's traveling squared, because it's rotating, divided by the radius. We do that math on there. We see, hey, we've got the total tension. So we've got a sine value, and we've got a cosine value. The only thing we really don't know at this point right now is the angle at which they're traveling. We haven't really calculated that because we don't know the total tension. There's two ways that we can go about calculating that. We can use the Pythagorean theorem, right? Or we can use trigonometry. Both will give us pretty much the same deal, 3.55 degrees. or I'm sorry, no, it's 3.55 degrees down. It's 86.545, something like that, off center. So we could do it either way, right? If we do it the other way, though, we'd have to swap the sine and cosine. So it's weird, right? No, wait, no, we would just have to change a few of the properties, like the G would have to be a negative G, and that would make it negative 355 degrees. But anyway, so we plug in our theta there. We can calculate the total tension now because we've got a theta. We could take either one. We could take the acceleration due to gravity times that mass and divide that by the cosine, or we can take that tension that we calculated in the x direction and multiply it by the sine. Both will give us approximately the same answer. It's like 0.639 newtons. And that doesn't sound like a lot if you don't know what a newton is. I mean, you're like, oh yeah, the newtons, it's the cookie, right? It's like, no, it's actually it's the unit that Newton created for force. And it's named after Newton, who was a smart cookie, but is not a cookie. You know, his mind was much greater than any little cookie. So 0.63, we'll call it 0.632 newtons. It's just a little bit more than what we got from our formula. We could have actually stopped at our formula for the tension and used that, but we want to be a little bit more precise, right? We want to say, hey, this is the actual tension. So the reason why that number is important is because there's some forces that are involved in this ball. I've already talked about the force of gravity, which is causing that dip to go from here to here, right? It's just causing that little dip. But there's more than that. See, the center of rotation, right? It's fixed. It's not moving. That means that all the forces that are being applied here equal 0. Now we have a tension going this way from that string pulling on it. So there has to be another force going this way that's going counter to that rotation, counter to that tension. If we take just a snapshot, that force is equal to the tension in the string. It's called the normal force. Now, the tube I know is made out of plastic, and the string, if it's a thread, the coefficient of friction on that is 0.5. Looked it up. You can look it up as well. It's right there. Force is equal to mass times acceleration. Now, that ball on a string that's doing 120 RPM is dragging a string across that friction force at 120 RPM, but it's only got radius about yay big, right? So the velocity goes down a bit. No big deal. But the force is still there, right? So what you gotta do is, now that we have it in motion, we have this force working opposite of that acceleration. That force is equal to the mass times the acceleration. Whatever that centripetal force is, the tension. The mass being so small, 4 grams, 0.004 kilograms, being applied, the force being applied to that small of a mass, right, means that the acceleration opposite of the motion must be very high, which means when equilibrium is set, when you let go and you stop spinning, this moment right here, All those forces come together. That ball that was here goes to here. It just instantly. It just drops down. That means that velocity just dropped. If we were to look at how many rotations it does, it actually doesn't even, if we can always put our hand out, stay far away from it, it'll just go, and it does like, I think like a half a rotation. It goes down and goes, and it stops after about, so far it just dies, goes down to zero. And the only way you could possibly keep it going would be if you were to pull the ball down, and not just pull it like steady, because steady pull will just keep it going, keep it staying where it's at, right? Which would be ideal, but that friction is slowing it down, so you won't see acceleration, because as you're pulling it down, that friction force is slowing it down. You're actually adding more friction by pulling it down. You've increased that tension. You've actually, whatever tension was on it, plus whatever you pull it down. So a quick jerk will do a quick burst of friction. So even though you'll see the acceleration go up, you won't see nearly as much as what you would expect. And what really is funny is that right before it gets down to where you'd want to stop pulling, it chaotically goes out of control. Either it's hit your hand or something. You hear all this clattering, it goes off. And every single instance where I've tried to do the experiment, I've gotten the exact same result. No matter if I pull it slowly, right? Where I pull it slowly, where I'm kind of equaling out the tension. The ball, well, if I pull with the full force of the tension that's on it, because the mass is so small here, and I'm essentially applying the force directly inward. It's not really adding any additional torque to the system, but it is changing that. But it's also adding that friction and all that stuff that comes with it. So if I pull it fast, I get it down to about right about maybe this much of a radius, and we lose it. It either hits the hand or something. You'll hear the clatter in all the videos that I've done. So that means that since this is like a full inch, this is 2.5 times what you're looking for your initial thing. So do the math if you want to. You can see how much the radius is reduced before we get uncontrollable chaos. And uncontrollable chaos is essentially what we call the area where physics fails. It's what we used to call the rotation of Mercury before Einstein, because it was so out of control. We were like, well, it's uncontrolled chaos. The physics at the time failed. Now, I think it's funny that he uses a conservation of rotational energy, because believe it or not, that's what Newton started with. He was like, well, if linear energy is conserved, rotational energy must be conserved as well. And he couldn't see any source for potential energy in it, unless you wanted to consider the tension in a string as a source of potential. But he was looking at that as just as being the source of the centripetal acceleration of force. See, a lot of people don't understand that. Energy is... we associate energy so much with motion, right? So a lot of people, they just automatically see, oh, the energy is equal to the motion. Energy, motion, energy, motion. There's also a thing called potential energy, stored energy, energy that has to do with position alone. This doesn't change, right? So when you look at, you look at the energy of the system, right? You have the kinetic energy of its motion, and you have the potential energy of its position. Now, when you lower the radius, if this is staying the same, and you lower and you change the position from here to here, if we consider this right here, the gray board here, we'll consider that the y plane, this the x plane, and this right here can be the z plane. We're not too concerned about the z plane because we're kind of already rotating around it already, and that's where our kinetic energy is involved in mostly, right? But when you pull here, you're exerting this force down. At this point here, God, cameras are hard to work with here. So at this point here, where your string is meeting your tube, that force is changing direction. It's going from here to here. And it's causing an acceleration from here to here. So we can see it's an acceleration in both the x and y direction. That sounds like a vector. Now, if we're going to do multiplication with this, we actually have to use what's called the cross product rule, which it means that you have to break up your vectors, assign the cosine and sine to each one of them as they go. It's not really hard. It's very easy. Your I components get multiplied with the I components. Your J components get multiplied with the J components. And your Z components get multiplied by your Z components if they're applicable in the situation, right? Then you take the answer there, and you should have a square on your component, but not on the number, right? So what that means, you have to actually square the magnitude there. You've already got the vector squared. You got to square the magnitude now. So you square that, and then because everything's squared, take the square root of all of that, and you'll have 3 different vectors. If your z vector isn't changed, like you haven't had any change in the z, that would actually come out to be 0. So you don't have to freak out about anything like that, you know, because we're not including z in this calculation. Z is 0 because we're taking a snapshot, right? That's all we can really do at any given point in time. We can only take a snapshot. We can't look at the video at point A, then look at the video at point B and say, see how they don't line up? Because we don't have a record of what's going on in between. We have to keep track of that. And what we want to do is we want to look at what are we looking at, right? So we look at the vectors, and vectors have magnitude and direction. Magnitude and direction. It's important, right? Because these different vectors, when you add them up, that gives you you'll see why when I show you. Because what you're looking for essentially is the total magnitude, right? And that's what we're getting at right now. So this will be fun. So, mass is not a vector. Mass is a quantity. You can add quantities to vectors, but you cannot add them willy-nilly. You have to actually partition them up so that your final thing, if you're dealing with a vector, you have to end with a vector. Momentum is a vector. Angular momentum is a vector. It has mass, quantities, and direction. So using the law of conservation of angular momentum, you can determine two pool balls, cue balls, whatever you call them, they hit each other and they ricochet off. You use the quantities of conservation of angular momentum, and you can figure out where that ball will be. And this works. I've seen it done. If I was a better pool player, I could show you how it's done myself, but I'm not that good. But essentially what it is if the ball's sitting here, right, nice and cool, and a ball comes at a certain velocity and hits it at a certain angle, two things here's what's going to happen is this ball will pick up some of the inertia of this ball, right? Some of its momentum. And that's essentially what it is. It's a transfer of velocity and inertia. See, this ball has a mass and velocity. The mass is inertia, right? When it's in motion, it becomes momentum. So it transfers that momentum. If they have the same mass and they hit at the right angle, they can actually become stuck together, and you'd see them going. And there's some interesting principles that go into that because the rotating against them adds more friction to the system, which slows them down a lot faster, which is why we usually talk about when they bounce off rather than when they stick together. As far as pool balls, like bricks and stuff like that, cars, they typically assume that they stick together rather than bounced off, because when they stick together, because friction isn't as much of a thing with that, the classroom scenario is usually that they stick together. Cars stick together, balls bounce apart. And that's the reason why, is because it's easier math to conclude, but at the same time, if you look at how soon it'll take for the cars to stop, that they always will use friction for that, right? The pool balls, they bounce apart, they say friction is negligible. Why? Glad you asked. Because the ball is rolling, it's not skidding, the ball is rolling. The coefficient of friction is static friction, and it's not being broken. It's not a factor in the motion too much. But still the ball slows, right? And that's because that coefficient there is still there. And a lot of times that we can even say, assume that it goes into the pocket at this point right here, right? Say the pocket's like 1 meter away, and they'll say, at what point will it go into the pocket, assuming friction is negligible. These are equations that are in the textbooks, right? And I can show them to you. It's not rocket science, right? It's just basic physics. I had to take it for my degree. I fucking loved it. I actually took an extra semester just because I liked it so much. So this idea that the angular energy is conserved, it's because it's dealing with that's kinetic energy. Kinetic energy gets transformed into all different kinds of energy. If you were to repeat this experiment several times within, say, a few seconds, right? Say you spin the ball around, pull it, let it go, pull it, let it go, pull it, let it go, like that. If you could keep doing that endlessly, right, until the walls broke down, and you were to touch the top of the rubber thing, supposing that it didn't have anything as far as melting or anything like that, it could feel really warm. There's a lot of heat energy being released there. Energy doesn't just come from nowhere, right? That heat energy is the result of friction. There's sound energy being created. When you spin that thing around, if you can get quiet enough, you'll hear a sound. going along with spinning it, right? That sound is energy being released from the system. Now, I'm going to go ahead and show everybody all the math that goes into all of this here, right here. So, I